Welcome, everyone. My name is Irfan Siddiqui, and it is my privilege to be the current chair of the physics department at the University of California, Berkeley. And I would like to introduce you to the 28th annual J. Robert Oppenheimer Lecture. The Oppenheimer Lecture annual series was established in 1998 and is made possible through the generosity of Jane and Robert Wilson, as well as the late Steve Krieger and his wife, Arlene. The series has brought a who's who of theoretical physicists to Berkeley. Past Oppenheimer lectures have included Mary Gell-Mann, C.N. Yang, Freeman Dyson, Helen Quinn, Charlie Kane, Leonard Susskind, Stephen Hawking, Kip Thorne, Lars Bilstein, and our own Marvin Cohen. The lecturers have come from many fields of physics, including particle physics, condensed matter physics, astrophysics, cosmology, AMO physics, and biophysics. Robert Oppenheimer was born in 1904, growing up in a upper middle-class family in Manhattan. He graduated from Harvard, majoring in chemistry, and entered Cambridge University in 1924 as a graduate student, hoping to work with Ernest Rutherford. In 1926, Oppenheimer left Cambridge to finish his PhD with Max Born in Göttingen. He published more than a dozen papers while with Born, mostly focused on the new theory of quantum mechanics. This included his most famous work, the Born-Oppenheimer approximation. This approximation that simplifies molecular physics by separating slow nuclear motion from the faster electron motion. I did not know we would have this explanation. There may be a test at the end of this approximation. Good. More than 90 years ago, in 1929, after 2 years of postdoctoral study, mostly in Europe, Oppenheimer returned to the United States. He accepted an associate professorship from Berkeley, where he remained for nearly 15 years. During this period, he published his most famous paper with Volkoff, establishing the Tolman-Oppenheimer-Volkoff limit on the maximum mass of a neutron star, the mass above which the star must collapse into a black hole. He also developed a theory of that collapse and black hole formation. Both topics are of keen interest today with the recent observation of gravitational waves from black hole and neutron star mergers. At Berkeley, Oppenheimer cultivated a culture of intellectual rigor among his students and colleagues. Leading a group of 8 to 10 graduate students and several postdoctoral researchers, he engaged with them daily, questioning their progress and pushing the boundaries of theoretical physics. Hans Bethe noted that probably the most important ingredient he brought to his teaching was his exquisite taste. He always knew what were the important problems. The scientific leadership would later shape not only his career, but also the course of history. In 1942, Oppenheimer was chosen to lead the World War II Manhattan Project engineering lab, sited at Los Alamos, New Mexico, near a ranch in which he owned. And of course, the ethical implications and the status of the world going forward was something he thought about for the rest of his life and was depicted for us in a motion picture that bears his name that many of us may have seen. Following World War II, Oppenheimer became a public figure, a symbol of the intersection of science and national policy. He graced the covers of Time and Life magazines, embodying the promise and perils of scientific advancement in the modern world. Yet this prominence came at a cost. In 1954, amid rising fears of the Cold War and McCarthyism, Oppenheimer was stripped of his national security clearance in a highly controversial hearing. A decade later, some measure of redemption arrived when President Lyndon Baines Johnson presented Oppenheimer with the nation's Fermi Award, a recognition of his scientific contributions and service to the nation. Oppenheimer's legacy at Berkeley is a simpler one, summarized by a plaque on the 4th floor of Physics South, with another quote from Hans Bethe. In these corner offices, 1929 to 1942, J. Robert Oppenheimer created the greatest school of theoretical physics the world has ever known, Hans Bethe. Berkeley Physics strives to continue this legacy today. Now it is my great pleasure to introduce my colleague, Professor Michael Zaletel, the Thomas and Alison Schneider Chair, who will introduce tonight's Oppenheimer lecturer, Dr. Ignacio Cirac. Professor Zaletel.
Thank you, Irfan. Good evening, everyone. Welcome to the Oppenheimer lecture. It's a real pleasure to be able to welcome Professor Ignacio Cirac to Berkeley. By way of introduction to his work, probably many of you have heard of quantum computing. Over the last couple of years, it's been in many headlines. It's been in government funding plans. It's the focus of major industrial effort to turn it into a real technology. At its heart, quantum computing asks whether the peculiar rules that govern atoms and electrons can be harnessed for a new kind of quantum information processing that could perform certain calculations or simulate quantum matter in ways that ordinary computers couldn't. But the idea of quantum computing actually goes much further back, more than 30 years, to the early 1990s, when it was still just a gleam in physicists' eyes. At that point, there were no companies or realistic machines on the horizon, and it was entirely unclear what a quantum computer would actually be built from. And Ignacio Cirac was one of the first people who helped show the world that this idea of quantum computing could be made concrete. In the 90s, he and his collaborators developed some of the first clear proposals for how a quantum computer could actually be built and controlled in the laboratory using the toolbox of atoms, ions, and light. These ideas became part of the foundation on which much of modern quantum information science is now built. But his influence also extends well beyond quantum computing to many aspects of fundamental science. He helped shape the paradigm of quantum simulation, which is what we'll hear about today, in which exquisitely controlled quantum systems like those being built in a lot of the labs here at Berkeley are used to simulate and understand seemingly unrelated physical systems in material science and high-energy physics. He helped lay the foundations of quantum communication, including ways of distributing quantum entanglement over long distances. And he's given us powerful theoretical tools for understanding how entanglement works, not just between a few atoms, but also in complex many-body systems like materials. He's opened many doors for the rest of us to walk through. Today, Professor Cirac is director of the Theory Division at the Max Planck Institute of Quantum Optics in Garching. His work has been recognized with many of the highest honors in the field, including the Wolf Prize, the Max Planck Medal, and as an elected international member of the U.S. National Academy of Science. Tonight, Ignacio will tell us about quantum simulation in the presence of errors, which I greatly look forward to learning from. So please join me in welcoming Professor Ignacio Cirac.
Okay, so thank you very much for this very kind introduction. It's my great pleasure to be here. So the first thing that I would like to do is to thank the organizers of this lecture for this very kind invitation. It's a great honor and big pleasure to be here. And as Mike mentioned, so I'm going to talk about quantum simulation in the presence of errors. And let me tell you what it is about. So I know that here there are some people who are experts on quantum computation. And there are people probably who have never heard about quantum physics, or just a little bit. And so I want to cover a little bit the broad spectrum of audience. And so that's why I'm going just to explain a little bit what is the title about, and then I will explain the in more detail. So you've heard that people are trying to build quantum computers today. So these are devices which try to solve problems in the same way as standard computers try to solve problems. So you give an input, and at the end, they will give you an output. And the difference with respect to the standard computers is that the information is processed in a different way. Instead of processing the information, just encoding it in bits, zeros and ones, it uses the laws of quantum physics in order to process this information. And it turns out that if you do it in the right way, then you can do some of the computations very efficiently, much faster than with standard computers. Now, there are only a few problems for which we know how to use quantum physics in order to speed up the process of solving these particular problems. But there is one that I think everybody would agree that that's the place where quantum computers will be very efficiently. And this is in solving problems that are of scientific interest, and it appears when we are describing many-body systems. So we have many particles interacting with each other according to the laws of quantum mechanics. So we use quantum computers in order to solve the scientific problems that are complex for classical computers, and that's the field of quantum simulation. So we are simulating like these complex problems with quantum computers. So that's what the title is about, quantum simulation. So solving difficult problems of physics now using quantum computers. Now, so these quantum computers don't exist yet, so we have prototypes, and one of the problems why we don't have quantum computers is because there are errors. So these computers have to work in extreme conditions at very low temperatures or very well isolated, and it's very difficult to do that in practice. So this means that while we are running a quantum computation, then there are some things happening that shouldn't happen, and this is what we call errors. And so what I'm going to talk about here is, so what happens if we are trying to solve one of these problems, complex problems with quantum computers, and there are errors while you're doing this computation. So on the one hand, you can think that because quantum computers are so powerful for this problem, then the errors, may not be that important. So still, they are going to be useful in order to solve problems that we cannot solve with classical computers. But on the other hand, since the quantum computer has errors, it means that they are not solving the problem. So they have errors in the solution. And so these are playing against each other, and that's what I want to show. So under which conditions we can show from the theoretical physicist, as a theoretical physicist, that these quantum computers would be useful even if there are errors during the computation, and how they will become more and more useful if you're improving the hardware and making less and less errors. Of course, in the long run, like say in the next 20 years or 10 years, something like that, these quantum computers will not have errors, hopefully. So all these errors will be corrected. And so you can think that my talk is about, so what will happen in the meantime until we have this called error-corrected quantum computers, whether we can still leverage the fact that we have this quantum systems, these prototypes, to make something that is, in quotes, useful. And useful here is defined by doing something that there is some interest in, at least in the scientific community, and that you cannot do with other equipment like the standard computers. So, let me explain you a little bit. So why it's interesting to have quantum computers solving these kind of problems. And so these problems, we call them quantum many-body problems, because what we want to solve, there are many particles interacting with each other, and according to the laws of quantum physics. So they appear, for example, you have a chemical compound, then the compound is composed of electrons and nuclei, and they are interacting with each other. Or they appear when you have some solid state, and which electrons maybe are moving and transporting electricity or maybe some magnetic properties. So they appear also in high energy physics. So you want to solve, let's say, standard model, and you try to solve it, and it turns out that you can express it as a many-body problems. So all these problems, even though they look very, very different from each other, have a common description. So at the end, if you want to make predictions about what will happen in these models, so the first thing that you do is that you put it in a lattice. So, for example, in the case of a solid-state system like this one here, since this solid state is composed of atoms that have some periodicity, then there's already a lattice there. And so what you have to do is to describe how electrons are moving on a lattice. In the case of high-energy physics, then you want to work in the continuum, but you want to put that in any computer, then you will have to discretize space, and so you will have a lattice, and then at the end everything is described in terms of a lattice. Or in chemistry, the same thing happens. So you will have to express in terms of some orbitals, and these orbitals can be expressed in terms of some lattice. So at the end, we want to solve these problems and make predictions about how they will behave under certain conditions. Then we have to, let me see. Oops. So we have the same problem. So at the end, we have a lattice. This is what is drawn there. And in this lattice, so you can imagine that you have a particle in each of these vertices of the lattices, like it's represented here by these blue balls. And at the end, so it turns out that you can describe this problem as a set of quantum particles, that are the blue particles, that are in this lattice. And so making a prediction about those systems is solving a problem of how these particles, we call spin 1/2 particles or qubits, behave on a lattice. Now, what changes from one problem to the next one, if we're working at chemistry, or we're working in solid-state physics, or we're working high energy, is how these particles interact with each other. And in the language of physics, we describe it as something that we call Hamiltonian. And so what is difficult and why there is a complexity in these problems when we want to make predictions in a standard computer is that now we will have to talk about what happens with these, let's say, particles in the lattice. So if I'm able to express how these particles in the lattice are behaving, then I will be able to translate and make predictions about the systems. So now if we had a classical problem, and then you imagine that these lattice particles just can take two values, so each of them can be in state 0 or 1, so this would be like a bit. Then, in principle, if you want to make a prediction, you have to know what is the configuration which will correspond to the prediction you want to have. So, for example, it may happen that if they interact with each other and there's a classical system, then after some time, they're in the state 0, 0, 0, 0, 0, 1, 1, 0, 0, there is one configuration. And if you're able to compute this configuration, then you will be able to make the predictions about your system. In quantum physics, the situation is much more difficult because we don't have a single configuration. According to the laws of quantum physics, you can have superpositions or configurations. So it means that these lattice particles, these qubits or these spin systems, now they will be in a superpositions of all possible configurations, meaning that they will be in 0, 0, 0, 0, in 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. So there are an exponential number of possible configurations, and the state of this system then can be in what we call in all of them at the same time. And now we want to make predictions, so what we will have to do is to see what is the probability, or we call it amplitude, of these configurations. So that's something that we write like that in the language of quantum physics. So if somebody tells us a problem, then at the end we will have to find what is the superpositions of all possible configurations. So at the end, this boils down to computing some complex coefficients, and one for each of the configuration. And just if you're not familiar with quantum physics, so if I'm able to compute these coefficients for each of those configurations, then I will be able to make the predictions and to tell you what will happen in the future, what will happen in thermal equilibrium, what will happen with the system. And the problem is that now, if I told you that there is an exponential number of configurations, like 2 to the power n configurations, it means that in order to make any predictions, I have to compute 2 to the power n coefficients. So the number of coefficients, in order to solve a problem, grows exponentially with n, where n is the number of, let's say, particles that I have on this lattice. It's like the volume of this lattice. And so if I want to put it in a computer, then I will have to store these coefficients, and then I will have to store 2 to the power n coefficients in my computer. And if n is of the order of 300, yes, so it's a very small system, 300, let's say, lattice sites, then I will have to store 2 to the power 300 coefficients. And this is such a huge number that, there will be no computer that can store these coefficients. So it's 2 to the 300 is something like 10 to the 80. So there's the number of barriers that we have in the whole universe. So it's impossible that we can store that in a computer. But not only that. So if I want to compute these coefficients, because I need to compute these coefficients in order to make the predictions, since they have to do at least one computation, one multiplication or something per coefficient, then I will have to do a number of operations which also grows exponentially with the size of the system. So again, if I have 300 particles in this lattice, then I will have to do 2 to the 300 operations, and at any clock time, and this will be completely impossible. And this is what it refers to when one talks about the complexity of many-body systems. So if I have one of those problems and I want to make the prediction, even if it's very small, then it takes an exponential resources, exponential memory, and exponential time to do that. And this is where quantum computers can help us, and that's something that was realized by Richard Feynman already in the 80s. And what he said is that, well, instead of computing these coefficients, actually, I don't need to compute these coefficients. So if at the end I want to answer the questions related to some physical properties, then why don't I use a quantum system itself, so it's these particles that I have in the lattice, why don't I use quantum particles, so qubits, and now prepare the state of these qubits in the state that solves my problem, and when I have that, I measure. So in a sense, what he was saying is that if I have a quantum system, why don't I have another quantum system that emulates the original one, and then if I have at the end this 300 qubits, then I have a quantum system with 300 particles, not 2 to the power 300, and I prepare the state, I do there the experiment as if I was the original problem that I want to solve and do the measurements there, and in this way I will get around the exponential problem. So this is how he invented quantum computation, and of course, I mean, if people found that there are other uses of quantum computers, other uses of having quantum systems in order to solve problems, but here I will concentrate on how with these quantum devices we can solve these quantum many-body problems. Okay, so again, so that's somehow that should be the message is that if we have one of these problems that I mentioned before that appears in chemistry or in solid-state physics or in high-energy physics, if I want to solve it with a classical computer, I will run out of resources. So as soon as the system grows, then everything grows exponentially, so I will not be I will run out of resources. However, if I have a quantum system, and I can solve it with a quantum system, a quantum computer or some quantum system that I can tame and prepare the state just by doing measurements there, then I can solve it and I can circumvent any exponential problem. So if I have to solve a problem of n qubits, then I will have to have n qubits in my lab and not 2 to the power n. And so that's why people say that quantum computation or quantum simulation, it's a place where quantum systems or quantum devices can help us a lot, because otherwise it's very difficult to solve that with classical systems. Now, during the last years, there have been many experiments on quantum simulation, so people who have used different platforms in order to solve some problems. And so in some cases, so they have observed that the problem that they were solving, if they tried to solve it with a classical computer, it would take longer time than the time that it took in the experiments that they were doing. And so that's why people are talking about quantum advantage, so that already with experiments they can do something that they cannot do with classical computers. And so I want to talk a little bit about that as well. But for that, so I have to say that now you want to solve these problems with quantum systems, like there are two incarnations, two different ways of doing that. One is to use a digital simulation. And so this would correspond to the case in which you not only discretize space, but also discretize time. And so you treat this quantum system in a digital way, just doing things one after each other. This is basically using a quantum computer to solve the problem. And the second is what we call analog quantum simulation. And the idea there is that if somebody gives you a problem, gives you this lattice, gives you how they interact, and if your lab, you have a system in which you can tame and make these particles interact in the same way as the problem that you want to solve, then you don't have to discretize time. You just have to switch on your system in your lab, wait, and then make measurements, and in this way you can answer the question that you pose. So these are two different ways, but they have also many similarities. And so in this talk, I will talk mostly about analog quantum simulators. They're easier to build than quantum computers, and they're more natural for certain simulations, but they have a problem, and this problem is that there exists no way of correcting errors in the system. So this means if you have this analog simulator, you have in the lab, you're trying to solve your problem in the lab with the simulation, and things don't work as you wanted, then there will be no way that you can correct the errors, so you will have errors in the result, and I want to talk a little bit about that. Now, so how are these systems in experiments? So now one example that I will be talking most of the time are atoms in optical lattices. So people are building quantum simulators just by taking atoms, making them levitate, just by using some laser fields, which push them and have them in some vacuum area. And now these atoms can move. So with a laser, you can make a lattice, and now these atoms can move in the lattice. And so they behave very much like electrons would move in a solid. So if you have a solid, I told you before, then the electrons will be moving, just jumping from one place to another one. And so in these experiments with atoms in optical lattices, they have a similar situation in which instead of electrons, they have atoms that are moving in these lattice sites. And then you can understand that these systems then simulates the electrons on a solid. So there is a very natural way of simulating with atoms in optical lattices problems that are related to materials. There are many other platforms in which people are doing quantum simulations. So here in Berkeley, there are several experiments doing quantum simulations with superconducting qubits, ion traps, there are some photonics, and so on. But most of the time, when I talk specifically about the quantum simulation, I will talk about cold atoms in optical lattices. So now I want to talk a little bit, reflect a little bit about quantum advantage. So I mentioned before that I want to solve a problem, let's say scientifically, so the ones that I mentioned before. I can do it with classical computer, I can do it with this quantum system, and I want to talk in which conditions can I say that I have an advantage? In which conditions do I say that my quantum computer or my quantum system in which I'm doing the simulator, it's better than the classical computer? And so, of course, this depends on many things, but so one thing is that what I can do is that I could run in my quantum system the problem, have a solution, even if it's ideal, and then I can try to run it in a classical computer, have the solution, and then compare the time in the two. And of course, this will depend on what is the algorithm that I use in my classical computer. And so, of course, what I can do is that I can just take all the algorithms that I know and compare with the one that is the fastest. And if my quantum systems, I solve the problem faster than with the fastest that I know for my classical computer, I would say that we have a quantum advantage. However, this is a little bit dangerous because this depends. So, what is the computer in which I run it? So maybe I use my laptop, and that's slow, and maybe I use a supercomputer or a GPU, and then this will depend on the computer. So that's why people, instead of looking at some particular instance of the problem, they look at the scaling. So they say, okay, so let me see if I grow my system, so what is the computational time that I have in a quantum computer? And if I grow my system, what is the time that it requires in a classical computer? And for example, if the time in my classical computer grows exponentially and the time in my classical computer grows linearly with time, then at some point, independent of the speeds, they will cross and there will be an advantage. So that's why people look at scalings in order to make the comparison, not at snapshots. The other thing that is important is that, so what does it mean that I solve my problem with a classical computer? So there might be somebody who says, well, I know a method that solves the problem very well, and it's a heuristic method. So people who are familiar here with fields, with quantum physics, maybe you can use Millfield theory, and it works very well for that problem. However, this is not a certified method. So if I have a quantum computer, then I promise that the result will be the right one. Whereas in a classical computer, you use a heuristic method, then sometimes it will work, and sometimes it may not work. And so the fact that you have a heuristic method that is very fast doesn't mean, you cannot compare it with another one that is certified. So in order to be fair, you should compare certified methods for the quantum system or quantum simulator and certified methods for classical computation. So that's, this will prevent me that say, well, I have a problem here that I can solve with my quantum computer very fast, and then somebody said, well, but if I do this and this and this approximation, then I also get the result, and I don't even need a computer. No, it has to be certified. You have to be able to make sure that this will work, and it's not that just by chance, knowing what is the result, then you just match the result. This also is a drawback, and the drawback is that when you say that you compare with the best known classical algorithm, it may happen that, there is one that you didn't try, and it's better than the one that you try. And so, or somebody on the next day discovers a classical algorithm, and that is better than your, faster than your quantum simulation or better scaling, and then, your glory just lasted for one day, because you say, I have quantum advantage, but somebody comes with something else. So this is why actually, computer scientists are very clever, and they solve it. They get around this problem in a very clever way. And so what they do is that they talk about complexity. So what they say is that, well, okay, so imagine that somebody comes tomorrow with an algorithm that is able to beat you and to have the same scaling like with your quantum computer. Then, if I formulate the problem completely well, then this makes that they can use the same classical algorithm not only to solve this problem, but to solve any problem that a quantum computer could solve. So in other words, so if somebody is able to solve this problem efficiently, then we don't need quantum computers anymore, because with this algorithm you can solve everything else. And so this protects you very much, because it tells you that it's a win-win situation. So it's very unlikely that somebody will come, because we believe that quantum computers are faster than, or better than classical computers. But in case somebody comes, then it's wonderful. You don't have to invest any money more in quantum computers, because this algorithm would be a better one. So here I will take the cap of a physicist. I will not talk about complexity, but when I talk about quantum advantage, what I will do is to compare with the certified best algorithms that we know. But there's the possibility of doing the formulation that we hear in terms of complexity, and so to make it much more robust, to what I will talk about here. Now, the other reflection that I want to make here is that when we talk about quantum advantage, everything that I said here is if there are no errors. But now, if we have an experimental system, then I mentioned before that things are not perfect, so there will be errors. So if we have these atoms in optical lattices, then with these atoms that are there, sometimes this laser fluctuates, and so they're not moving in the same way as they should be. Or in other words, the interactions that I'm simulating are different from the ones of the problem that somebody posed. And so there are errors. And so now, what happens if there are imperfections? So what does it mean then, quantum advantage, if there are errors? So this means that now when I'm answering the question, so for example, I want to make a prediction, so how this system will evolve or what this reaction will happen, then my answer will not be perfect. So I'm not answering the question, I'm giving you a wrong result. So if you want to be fair, now you should also allow the classical algorithm to make errors. And so you should compare now, so the two devices, but now if they have errors. And so what does it mean then, quantum advantage in this case? So just wanted to mention that, because when I talk about quantum advantage, then because these things will pop up. Now, so the other question that I wanted to briefly mention is, so what are the problems? Now, I said, well, you want to solve some problems in many-body physics and so on. Well, there are many problems that you can try to solve. So one of them is what happens in thermal equilibrium. So you have a system, and what happens if it's at certain temperature, you want to measure if it will conduct electricity or if it will be magnetic or not. So here I will concentrate in what we call dynamical problems. So this is a problem in which we start with some initial state, then we change the system, then it evolves, and I want to predict a property, a physical property, after some time t. So it means that I have some property that I call O, and I want to compute after time t. And so that's how we pose the problem. And so that's what will be important later on, is that somebody gives me the time for which I want to make the prediction. This is this capital T, and this property, physical property, which is O. Now, because if we want to formulate it properly, somebody has to tell me, so what is the lattice that I have? What is the Hamiltonian? What is the initial state? And so on. So there are some details there. But what is important here is so what is the time and what is the property that I want to know? And now, okay. And actually, so I will be interested in knowing what is the expectation value of this property. And actually, so this will depend on how big is my lattice. And so in physics, in many problems, like in condensed matter physics or in high energy physics, you are interested in what we call the thermodynamic limit, in the limit where the lattice is infinite. So what I want to predict is, so what happens if I have like an infinite system, an infinite lattice, I check it, and I wait for a time, and I want to predict, so what is a physical property? And this physical property is so what happens with one of the qubits? Okay, so it's what is the magnetization of one of the qubits. And of course that's the way that we represent in quantum computation this problem. So we start, so this is a diagram, a time diagram that goes from left to right. So it means that we have qubits in the lattice, here represented in one dimension. So they start in some initial state, so in state 0. Now, there is the evolution. This is what is represented here. And after some time, I want to know what happens with one of the qubits, and I want to predict, so what will be the expectation value of this qubit. And because you can think of some other questions, not the dynamics, but thermal equilibrium, but I will not deal with them here to make things simple. So what's going on? Okay, so I will start talking about, so what happens if the quantum simulator that I have is ideal, no errors. I will make some statements, and then I will say what happens if the quantum simulator has errors, and then make some other statements. So I start with the ideal device. And okay, so again, the problem statement now, I can, if I want to talk about quantum advantage, I can formulate it in this way. So this is the goal. So I'm interested in this property after some time. And now imagine that I have a classical algorithm, and it gives me certain result, which I call O classical. And it takes a time. So this is the time that the algorithm runs, and takes a time that I call T classical. I have a quantum algorithm for my quantum device, and this gives some other output. It's an estimator, and it takes some time, which I call T quantum. And the question is, giving an accuracy, what is the computational time in order to be that my prediction is close to the exact one by this accuracy? And of course, so I want to get some accuracy, and I want to compute what is the time that it takes in a classical computer, in a quantum computer. And now, this time in a classical computer and a quantum computer will depend on T. T is the time of the simulation that I ask you. I don't want you to ask something after a time T. And so it may happen that this scaling is, for example, polynomially. Imagine that in a quantum computer, then the computational time to get that, it's like proportional to T. And it may happen that maybe the classical one is exponentially. And if this is the case, then we have a clear case of quantum advantage, because because this means that if I ask you to run it for longer and longer times, then the classical computer at the end will fail because of this exponential growth of time, the computational time, whereas in the quantum computer, it will run for arbitrarily long times. Okay, so now I want to explain how you show that this is the case, so that in a classical computer it takes an exponential time, and in a classical computer an exponential time, and a quantum computer it's a polynomial time. And this is related to something which is called Lieb-Robinson bound. So it's a mathematical result that was derived many years ago. And the basic idea of that is that if we have some interactions, even in a quantum mechanical way, things take some time to propagate. So if I am here and somebody does something very far away, then I will notice that after some time, because the things have to propagate here. So this means in this drawing that if I want to measure what happens here, then actually this cannot depend, what I measure here cannot depend on something that is very far away, because there was no time in order to affect my result here. So this is what is called the Lieb-Robinson bound. And so this means that only the qubits that are here are the ones in this kind of cone, are the ones that are going to affect my result. And so it means in practice that actually the fact that I have an infinite system doesn't matter at all, because most of the qubits will not affect my result here, so I can take here some finite number of qubits, and if I take this finite number of qubits, I can solve the problem, even if the infinite limit. And so the number of qubits that I have to take here has to be proportional to time. So now it means that at the end, if I want to solve this problem, I will have to take a number of qubits which is proportional to time, and this depends on the spatial dimension. So if I have now a problem in 2 dimensions, then because it will propagate in 2 dimensions, so what I will have is that I will have to consider L by L qubits, in which L is proportional to time. And if we want to solve this problem of L times L qubits with a classical computer, then I told you at the beginning that we need a computational time that grows exponentially with the number of qubits. So this means that the time that it will take me to solve this with a classical computer will run as 2 to the power of the number of qubits. The number of qubits goes like L to the power of the physical dimension that I have, and this goes exponentially with time. And so this is why, in a very simple way, you can solve this problem, even in the thermodynamic limit, in the way that I formulated, but it takes an exponential time with the computational time. So the computational time for a classical computer will grow exponentially with the time that I'm asking you to do the simulation. However, if you have a quantum computer or a quantum simulator, then you can still take these L qubits. You can go to your lab, take this L by L qubits, L to the D qubits, and just let them evolve and make measurements, repeat it several times, and with that you will make the prediction. And so in this way, this means that the computational time in a quantum computer will grow polynomially, actually linearly with time. And so according to what I say, then we say a clear case of quantum advantage, because to solve the problem as I pose it, then in a classical computer, the computational time grows exponentially with this t, and in the quantum computer it grows polynomially with t. And this is what I told you, that independent of what is the computer that you use, at some point they will cross, and then you can say that we have quantum advantage. Now, this was without errors. I'm going to introduce the fact that in these experiments there are errors, and I'm going now to analyze the same thing with errors. And so that's what is represented here. This is my quantum simulator. In the quantum simulator, the ideal one, this is my device, maybe my atoms in optical lattices, but in reality, this is not perfect. So this lattice fluctuates, maybe they depend on time, there is dissipation. And so what does it mean? Well, what this means is that now my quantum computer would not have like the evolution, the ideal evolution, and that's something that we know how to model very well. So what we can write is a differential equation that will tell you so how the quantum computer or the quantum systems evolves now in the presence of errors. And so the only thing that matters here is that the error here is characterized here by this capital gamma. And so what is now is that the changes now from what we had before is that there is some error rate. This gamma is the rate at which the error occurs at each qubit. So if I have a very good hardware, this gamma will be very small because the errors will occur at a very small rate. But if I have a very bad quantum simulator, then this gamma will be large. And so now what we want to see is what happens if we have some gamma. And so you can now go to the same picture that I had before, in which we say, I only need to know what happens with these qubits here, because, leave Robinson bound. And now, whenever there is an error within this area here, then this means that I can get the wrong result. So, as you see here, the result will be accurate as long as there is a very small probability that there is an error in this area, because then, in that case, it corresponds to the ideal case. And so you can see that the error will be so proportional to the area that we have here, and this area will proportional to the error rate times the area. So it scales like the error rate times the time to some power. And so if I ask you to run my simulation for a long time, then at the end it will give you the wrong result, because for sure there will be an error there, and so I will have a wrong result. So this means that my quantum simulator will only be reliable up to some maximal time. And so you can just take this formula, and that you see that the maximal time will depend basically on how much is gamma. So if gamma is 0, then this maximal time can be as long as you want. But if you have some error rate, then you can only trust the results for a certain time. And so now you want to make a fair comparison with a classical computer, then what you can ask, so the question in this context is, so since in my quantum system, quantum device, quantum simulator, I can only run for some time t, so I can only make predictions for this time t, and if I tell you that I have some accuracy epsilon, so what is the computational time to reach the same accuracy in this time? So I'm asking you a classical computer to get the same accuracy that I can have in a quantum computer for the maximal time that I can have in my quantum computer. And now it's very simple to see that in a classical computer, this classical time, we said before that is exponential on this T maximum. So this means that this would be exponential in 1 over gamma. And in a quantum computer, however, we say that the time is polynomial in T maximum, so this time will be polynomial in 1 over gamma. So what else does it mean? So this means that, so let me give you an example. So imagine that I'm doing I have my quantum system and I have some error rate, and I produce this result for some time with some error. And now you have a classical algorithm, a classical computer, which has a number of elementary steps in order to get the same result as with my quantum computer. Let's say 1,000,000 elementary steps. And now I go to my hardware and I improve the error rate, for example, by a factor of 10. So I improve my hardware, and then I have that gamma is gamma divided by 10. Then this means that in your classical system, then the computational time would be the one that you had before to the power 10. So if it was 1,000,000 now, if I improve by a factor of 10, I would be 10 to the 60. So what it means, this result, what it means is that it will be very difficult for a classical computer to catch up with the improvements of the hardware, because the computational time in a classical computer will grow exponentially with the factors that I'm gaining in my lab. So if you improve your hardware better and better, then at some point, then you will be able to have some results with your quantum computer that it will not be possible to have with your classical computer. So that's what I said before. So I think we still have about 10 minutes. So now, so what I was explaining was related to an analog quantum simulator. So it means that somebody, again, comes with a problem, tells me what is the problem, then I go to my lab, has, for example, these atoms in optical lattices, and I have to engineer the interactions of my atoms in such a way that they resemble the problem that you gave me. Now, this is not possible in many cases. So, for example, atoms in optical lattices have two-body interactions, so the interactions are like paired interactions. And some problems that you want to solve, like, for example, the ones that appear in high-energy physics, they have four-body interactions, so it means that you cannot simulate it in your lab. But people have figured out how, even though you cannot have these interactions in your system, you can still use an analog simulator in order to do that. And these are different techniques and that people use that. So one of them is called trotterization, another one is called perturbation theory, another one is Floquet. And so the idea, for example, in Floquet is that maybe in my lab, I cannot engineer the interactions that they have, but what can have is I can engineer some other interactions, but I can make them time dependent. So I can change the interactions as a function of time. And it turns out that if you change them very, very fast, then it's almost equivalent to having the original interaction. So even though I have two-body interactions, if I change as a function of time, then they behave as four-body interactions. Or in trotterization, the same things, that even though you have two-body interactions, then at the end, they behave like if you would have like some other kind of interactions. And so let me just give you the example of trotterization, which is probably one of the most relevant. Imagine that I have somebody gives me a line that's a simple problem in which you want to understand. So what happens is you have a line of atoms interacting with each other according to some Hamiltonian. In this, Hamiltonian makes pair interactions between nearest neighbors. And imagine that in your lab, you don't have access to this particular Hamiltonian. You cannot engineer, but what you can do is to engineer maybe the interactions between this pair, this pair, this pair, this pair, this pair, this pair. So this interaction you can engineer, and at the same time, you can engineer interactions between now this pair, this pair, this pair, this pair. So not both of them at the same time, but just one and the other one. So what you can do is that instead you want to have all possible interactions, what you can do is switch on one interaction and the other one, then one interaction and the other one. And if you do that, then it turns out that if you do sufficiently fast, then the evolution is equivalent if you will have the two interactions on all the time. And in fact, that's what people use in order to discretize time and to put problems in quantum computers. So you do this in general with more complex Hamiltonian, then you can take any Hamiltonian and at the end express it as a quantum circuit that has just two-body interactions, analog and digital. Now, if you look at this problem, and so now you want to do the same analysis that I said before, then you face a problem. And the problem is that now if you're doing these interactions, so instead of putting all of them on at the same time, then you're taking one and then the other one, then it's not exactly the same. So there will be some error, and then you can compute what is the error in this approximation. And this error actually turns out that for each of the time steps in which you are doing that is proportional to the system size. So in order to make this error small, then you have to make many small time steps to make an error small. But if you have many time steps, then in each of the time steps you can make errors. So you have many errors occurring. Or if you want, what you have is a quantum circuit in which you have many gates, and you have to put, the system is bigger and bigger and bigger, you have to put more gates, so you're putting more errors, and then at the end, so this will explode. And so that's something that, I mean, one can think that this will happen, and this means that quantum simulations, if you don't have the native Hamiltonian in your lab, then will not be possible because of this accumulation of errors. However, this turns out not to be true, and the reason is that actually this approximation that tells you that this is proportional to the system size and that you have to make smaller steps, then you can take into account that actually your system is not infinite, because I told you before that you can cut it. And so you can cut it, then you don't have to care about the total size of your system, and then you put it back in the formulas, then it turns out that this is not a problem. And so, well, I mean, I wanted to show some numerical results which show that, but at the end I will tell you so what happens. And so what happens is, in all these cases, what you can show is that the errors that you have still scales like the error rate, you have some errors, times the total time of the computation, and the only thing is that the error rate appears to some power. So before it was the error rate times the time to some power, now it's the error rate to some power. So the only thing that changes is this power, so all the conclusions that I told you before still hold. So the only thing that there is a different dependence, but still this advantage that I was mentioning before in classical and quantum systems stand. So again, so the message is that whatever you have in an analog quantum simulator, if you have the native Hamiltonian, or you have to discretize, or you have to put it in a quantum computer, in all cases there is this crossover at which if you improve the quantum computer, your quantum simulator, then at some point the quantum simulators will win like an exponentially with respect to classical computers. So I guess still have 5 minutes, and so I wanted to mention something about Oppenheimer in my talk, and so that's why I'll talk about quantum simulators, but in a different context now. I go back to these cold atoms in optical lattices, and so it turns out that for the experts here, so probably you noticed that when I'm talking about these quantum simulations, I was somehow concentrated on problems in condensed matter physics and high energy physics, but not in quantum chemistry. So the problems in quantum chemistry are quite different, because when we have this lattice and we put it on the lattice, as I told you before, then it turns out that in this lattice is as if they would have long-range interaction. So the qubits that are very far away, they can talk to each other. And this means that what I told you before about this Lieb-Robinson bound is not true there, because there can be like a very fast interactions between parts that are very far away because they are talking to each other. So what happens now with chemistry problems? And so in the past we have been thinking about how to do quantum simulations of chemistry problems with atoms in optical lattices. And so the idea that we were pursuing is to do it in the Born-Oppenheimer approximation. And so this means that this Born-Oppenheimer, so it means that so you have a chemistry problem. So you have a nuclei, another nucleus, and you have electrons, and then they form, for example, a molecule. So in this approximation, you assume that the mass of the nucleus is so big that they don't move, or that they move like a classical particle. So the only particles that you have to take into account are the electrons, because the other ones are fixed. And so then it means that you can write now your Hamiltonian, in which the electrons are attracted to the nuclei and the electrons are repelled from each other. And so now you, for example, can fix the position of your atoms, then solve this problem, so find what is the lowest energy and plot the energy as a function of the distance between the nuclei, and this will give you the molecular potentials, and in this way you can study some molecules. So, how can you simulate these problems with atoms in optical lattices? And so you say, well, I mean, imagine, well, the first thing is that instead of electrons, I can use the atoms. And so these electrons are fermions, so I can use fermionic atoms to do that. And now the atoms have to be attracted to some places, like where the nucleus are. So what I can put is some laser potential which pushes the atom towards some places. And so this would simulate the fact that you have the electrons just moving around the nuclei. But the problem comes, so how do you make these atoms to interact with each other, to repel, like the electrons repel? And so you know that the electrons repel with each other with a Coulomb interaction. But these atoms are neutral atoms, so they don't repel. They only interact if they are close to each other. And so we were thinking about how this can be done in practice. And so we came up with the following idea. And it's to imitate what happens in nature. So when we learn that that electrons repel from each other, this is like an effective interaction. So if one takes quantum electrodynamics, then it turns out that these electrons interact with each other because they exchange photons. So they are interacting with the electromagnetic field, and because one electron interacts with the electromagnetic field, this electromagnetic field is interacting with the other electron, and effectively this gives rise to the repulsion. So you can think of that if you have two electrons and this emits a photon, then it gets a recoil in this direction, and if this absorbs the photon, then it gets a push in the other direction. So this is like if they are repelling from each other. And so what we thought is that you can do the same thing with atoms in optical lattice. So in order to have an interaction between atoms that would have this repulsion, what you can do is to put some other kind of atoms, bosonic atoms, which play the role of the photons, and in this way to simulate the interactions. And we found what are the conditions to do that, but it turns out that that's quite difficult in practice. I mean, in theory it works, and paper works, but experiments are very difficult. And during the last year, so we try to simplify this in order to make it more experimental friendly. So we first thought that now what you can do is to start having atoms that interact with each other because they are taken to some Rydberg state, and in this Rydberg state they have they interact. They are like small dipoles that repel each other. I mean, the problem there is that this repulsion goes like 1 over r cubed, is the distance to the cube, not 1 over r, so it's not like Coulomb. But still, so what we found is that the phenomenology is very, very similar to the ones that occurs in chemistry. So you will have like hydrogen atoms, hydrogen molecules, potentials, and things like that. And so what we have done very recently is to say, so can one do simulations now using atoms in optical lattice, not of static problems with the Born-Oppenheimer approximation, but beyond the Born-Oppenheimer approximation. So you can think of that you would like to have an experiment in which you have an atom here, which is a nuclei and some electrons, and an atom with nuclei and electrons, and then they collide with each other, and at the end there's a chemical reaction, so maybe this captures some of the electrons and the atoms, and so we figure out how you can do things, experiment of that kind now using atoms. So the idea is that you can have now, apart from the atoms which are emulating the electrons, you can have another atom which emulates the nuclei, and you can have interactions among them such a way that they are attractive between electrons and nuclei, repulsive between electrons, and repulsive between nuclei. And now you can even put some velocities, you can create some superposition such a way that there are velocities, and then have experiments in which you resemble with neutral atoms, so something that will happen, you have molecules. So with that, I would like to finish. And so the take-home message of my talk is first, I mentioned at the beginning that among all the applications that we know for quantum computers, so quantum simulation is the most clear one. So it's a one in which because the problems that we want to solve are quantum mechanical, they are very badly suited for classical computers, very well suited for quantum devices. And so quantum simulation is the place where we expect to have the results where, let's say, these quantum computer simulators are useful as compared to classical devices. I also mentioned that even if there are errors, you don't have to correct them. What you have to do is to improve the hardware, and at some point you will improve the hardware and it will be impossible to catch up with classical devices, so you will be able to answer questions that you cannot answer with classical systems. And that's what I mentioned before. And at the end, I was talking about a distinct regime of experiments with cold atoms in optical lattices, in which they can explore some phenomena that are not exactly like the ones in chemistry, but are connected to chemistry. And they are not exact, the ones, because the interactions between the electrons is not Coulomb interaction, but is an interaction that is 1 over r cube. It's like you have chemistry in which instead of Coulomb interaction, you change the law, and that's a different one. And that is the kind of experiments that you can explore with the systems. And with that, I would like to thank my collaborators, especially Raúl Trivedi and Alhan Franco Rubio, who were, the results that were related to the errors in quantum simulation were in collaboration with them, and all of you for your attention.
Thanks for the wonderful talk. Yeah, my question is about, for the error models, you mentioned that you always kind of said it's okay, Lindbladian errors. Do you think if the conclusions hold, if you relax that assumption and it became, let's say, non-Markovian or coherent errors, do you think this exponential versus polynomial advantage would remain in the presence of non-Lindbladian errors?
Yes. So in fact, I mean, in this Lindbladian, it contains, it's a technical statement, so it contains Hamiltonian terms of coupling within auxiliary systems. So it's very general, the interactions that we consider. So the only thing that we are imposing is that these errors that you have, let's say you have unbounded operators, meaning that you cannot have like an infinite interaction with your environment. But as long as there's a finite interaction with your environment and is bounded by this gamma, then this is what appears in your formula. And the other condition is that it has to be local. So the errors have to be local. So they can, I mean, an error somewhere else can affect you here instantaneously. Then what I say is not correct.
For your foundation in using cold-trapped ions as a foundational thing for quantum computing, how did you come across it, and how did you manage the magnetic field interference with ions?
Sorry, with ions?
How did you manage the magnetic field interference with the ions?
So how do I manage to have a magnetic field in the case of, no, sorry.
How did you manage magnetic field interference with the ions when using them as the foundation for quantum computing, since it was one of the your main research? Okay,
I see. So, well, in quantum computation with ions, it's different from the cold atoms in optical lattice that I mentioned here. So in the case of atoms in optical lattice, I mentioned that what you do is that you use lasers to levitate them, and then they can move. In the case of ions, you don't use lasers to levitate them, but you use some electric fields, so some so it's called ion traps, which is based on an electric fields. And so once you have these atoms, these ions levitated, they have some internal state. This is the spin. And so what happens is that if you now use lasers, then you can make that they interact with each other and you can engineer this interaction. And in particular, you can simulate the presence of a magnetic field just by putting a laser. And it turns out that the laser will try to align these spins in the same way as a magnetic field. So just by using laser fields in the appropriate way, then is how you can engineer these interactions to emulate the problem that you want to solve.
Hello, thank you for the really good talk. I have a question where, have you or others been thinking about, so for context, we can maybe in the future, right, network different quantum computers via like non-local entanglement. And have you or people been thinking about what analog quantum simulations will look like in a world where we have networked quantum computers?
Okay, so like 15 years ago, we wrote a paper about quantum simulation in remote quantum computers in such a way that maybe your quantum computer is not big enough to simulate the whole system, so you can divide in different systems, and then you can make them interact through some connections, some optical connection. So in principle, I mean, that's a way that you can scale up your systems. However, it's very difficult in practice. So in principle, I mean, you can have like different computers that are connected and distribute, let's say, your quantum simulation. However, I guess that this will take some time to have something like that in the labs.
Thank you. A question, looking into the future, to what extent will the ability to fabricate fiber optics in much smaller diameters and complex arrays be a foundation for milestones in the technology for quantum computers?
Okay, so there are different platforms in which people are building quantum computers, and some of them then probably they will not depend on the better fibers or smaller. But in some ones, they are very important. So especially in the ones that are based on atomic systems, because in atomic systems, you have many atoms. You have to trace each of the atoms with an individual, let's say, laser field, and this has to come from some optical fibers. So the improvement of optical fibers in whatever means to making them smaller, making them the beam ways smaller and so on, this will, of course, be crucial in order to scale up certain kind of quantum computers, indeed.
Hi, you touch up on the fact that there could be errors, especially in a quantum simulator, that the chance that you could have error in your circuit scales polynomially with the size or the evolution time of the circuit. To my understanding, in most gate-based quantum computers, people do envision some kind of error correction code to do it, but since you're also pointing out the analog simulators could be the near-term goal or as powerful, is there a similar way of doing error correction that you can kind of envision to mitigate these errors?
Okay, so two statements. So first of all, as far as I know, there is not an error correction. There are not error correction methods for analog quantum simulator. The other statement is that if I have a quantum computer and it has errors, then everything that I talk about here applies. It corresponds to what I call trotterization. So now if you're correcting the errors, so you're doing error correction, and even though it's not fault-tolerant error correction, but it decreases effectively your error rate, then it goes in the right direction. So this means that it will be much harder to simulate them, exponentially harder with a classical computer. So in the case of digital quantum computation, correcting errors is a way of improving hardware without having to improve hardware.
What are the original sources of error, and how do you identify if a calculation is erroneous after it's completed?
Okay, so now it depends on the platform, but for the cold atoms in optical lattice, there are different kind of errors. So first of all, these are atoms. When I talk about the qubits, then the qubits, so typically you take hyperfine states, and these hyperfine states, if there is some random magnetic field or some antenna coming from something, it can change. So it will, change your state even though you don't want to change it. The second thing is that in order to make interactions, so in order to engineer interactions, so typically what you do is that you bring these atoms to some Rydberg state or some excited state, and so this can be the spontaneous emission decay, and so spontaneous emission decay is another source of error. Top of that, your lasers that are forming this lattice may vibrate a little bit, so they have amplitude and phase fluctuations, and they produce errors. It can also be that these atoms have to be in vacuum, because otherwise, if there is a molecule can collide with your atom, but the atom, vacuum is not perfect, and so it may be some molecule that goes by. So you see there are many errors that you can classify, so you can look at what is the rate of each of them, and then there would be some of them that are not important, some of them that are important. And so that's why when people, this is what they do in practice, when they do experiments, they concentrate on the most important errors, and so they try to improve that, and then they're facing the next one, and then the next one. So correcting, improving the hardware means that you have to go one by one through all the errors and trying to improve them.
First, thank you for a great talk. Going back to Alp's question about these types of errors that may or may not be captured. So you have this great gamma in front. What if gamma is time dependent? And does that establish some hierarchy of time scales? And are there other pernicious quantum errors that are not in your Hamiltonian if you get out of your computational subspace, for example?
Okay, so this can be time dependent, but if you put some conditions on how this time dependence is, then still falls into this description. So what it will not fall is, for example, you have very, very fast time dependent, because it's equivalent as if there is coupling to something very strongly. And so there are frequency fluctuations that are very fast. This will not work. So that's a limitation indeed.
So it sounds very promising that you're able to get an exponential improvement once you get your error rate down to a good enough number. Do you have a sense of how good that error rate needs to be until when the quantum computers are better than the classical computers?
I think that the error rate would be of the order of, let's say, 10 to the minus 3, whatever it means. I mean, that you have to compare it with something, and this compare to the terms of the Hamiltonian, which are the good ones. The bad ones are 10 to the minus 3. I mean, this already would make it, I guess, very hard for classical computers to catch up. I mean, that's just a number that maybe it's, this is typically the number that thing would be real. I mean, where I would expect that then you can really claim that it will be very hard for classical computers to get the same times with the same error as a quantum computer in, let's say, so reasonable computational time.
Great. Thank you very much. Good.